Humanity is in the midst of expanding its reach into the orbit of Earth and beyond. One of the primary tools that is enabling this outward expansion are electric propulsion devices, like Hall effect thrusters, which are the most flown in-space propulsion device ever. Unlike conventional chemical rockets, these devices operate on gas propellants and plasmas, combined with thermal, electrostatic, and/or electromagnetic effects to accelerate their exhaust to extremely high speeds. This aspect of EP allows for a combination of fuel economy and efficiency that makes these devices well-suited for in-space propulsion applications. If these devices are so great, what's stopping us from using them to go to Mars, say today? Many electric propulsion systems are well characterized for xenon operation. However, this propellant is rare and expensive and may not be optimal for long-duration propellant storage architectures. This means we need to consider other, less characterized propellants. The first group to consider are metals, which can be stored easily as solids with comparable ionization energies to xenon. It has been proposed that these kinds of propellants could be optimal for crewed or cargo missions for interplanetary travel. The second category are molecular propellants like air or water. Electric propulsion operation on these propellants could be the key to so-called air-breathing operation. Unfortunately, laboratory characterization of these devices on non-noble propellants is limited, with flight heritage being even less. Another outstanding problem is that many of the most mature electric propulsion devices are unable to be predictively modeled due to anomalous electron transport. To begin to tackle these problems at the Plasma Dynamics and Electric Propulsion Laboratory, we leverage non-perturbative laser measurements of electron velocities in the discharge plasma of our devices. The particular technique we use is called laser incoherent Thomson scattering. The basic principles of this diagnostic are as follows. Just kidding, although the laser is pretty scary. Instead, we direct a 10-watt laser into a small scattering volume inside of the plume of one of our thrusters. As this energy, in the form of photons, enters the plasma, a scattering event will occur between a photon and an electron. After this collision, the photon will then be re-emitted at some semi-random angle. We can zoom out to see our diagnostic in action, and note it is crucial to choose a fixed scattering angle for two very important reasons. The first is due to a Doppler shift that will occur as the measured photon shifts from the electron to the lab frame of reference. It turns out that the correlation between this Doppler shift and the electron's velocity magnitude is a function of this scattering angle. Secondly, the laser incoherent Thomson scattering diagnostic will inform on electron velocity parallel to the difference between the scattered and initial wave vector. By knowing our scattering geometry, we can then deduce which component of the electron velocity we measured and design our experiments with this in mind. Once we collect this signal, the light traverses an optical bench that consists of a series of volume Bragg filters, which attenuates much of our stray light, a spectrometer, which spatially separates the Doppler-shifted wavelengths, and then a camera, which measures our signal. We expect our velocity distributions to look something like this, which, if we assume thermal equilibrium, directly informs us of the electron temperature, density, and drift velocities at the location we pointed our diagnostic at. Recently, our lab has produced results with this diagnostic that suggest that electrons are adiabatic along magnetic field lines in Hall thrusters. This challenges some of the most foundational assumptions made about electron behavior in these devices. This technique offers a rarely seen glimpse into how the electrons are behaving in our thrusters, which is crucial for understanding the basic physics for these devices, while also informing on these changes as a function of propellant type. With this new data available, a new frontier for electric propulsion operation on unique propellants and modeling is around the corner.